Imagine this. You're preparing to snack on a new pack of Lay's chips, only to find out that there's a lot of air inside it. What you don't know is that it's not actually air, it's nitrogen gas, which is unreactive and prevents the chips from becoming spoiled. Now, before you give Lay's too much flack for having 42% nitrogen in their bags, did you know that a bag of Cheetos has 59% nitrogen in their bags? Yes, that's right. Why do manufacturers pack in so much nitrogen into their bags of chips? We'll find out in today's video, so stay tuned. Assalamu alaikum everyone, this is Fahd Ansari and I'm here to help you conquer chemistry. Before we begin today's video, just a reminder that over 70% of you still haven't subscribed. So if you're one of those people, do push the subscribe button and press the bell button for notifications so that you don't miss any videos. Let's get started. So in previous videos, we talked about covalent bonds, and if you haven't any idea what a covalent bond is, you should watch the previous video before getting to this one. So we'll be discussing two types of covalent bonds. The first is the sigma bond. It is formed by the end-on overlap of atomic orbitals. Atomic orbitals we've also covered in a previous video, and in this video we will be talking about s and p orbitals in particular. So first case is the overlap of s orbitals, right? So we have a hydrogen molecule H2, right? And hydrogen has the electronic configuration of 1s1, and we know that the s orbital is spherically shaped. So if I draw a nucleus over here, surrounded by the spherically shaped s orbital, I'm drawing in the axes just to show that this is a three-dimensional figure, right? So this is the s orbital in the first principal quantum shell for hydrogen atom. So what I will do is I have two hydrogen atoms with their nuclei and their 1s orbitals. Now when these get together, what happens is if I divide this s orbital into two ends, so we have this end and this end, which are facing each other, that overlap for end-on overlap to form a sigma bond, right? So when I make these two together, what happens is that I get something that looks kind of like this, right? The s orbitals, the two ends facing each other of these s orbitals of the hydrogen atoms have overlapped to form this giant blob that is called a molecular orbital. And the shared pair of electrons, the bond pair, resides in between the two positively charged nuclei, these two dots, and this dotted cross, the bond pair, is attracted by not just the one nucleus of this hydrogen atom, but the nucleus of the other hydrogen atom as well. And these forces of attraction are your covalent bond, right? So this is the overlap of s orbitals to form a hydrogen molecule. So the second case is the overlap of p orbitals in fluorine, right? In fluoride gas, fluorine has a proton number of 9, so its electronic configuration is 1s2, 2s2, 2p5, right? So in this 2p subshell, we know that two of the p orbitals are complete and one of them only has one electron. So it is that incompletely filled p orbital in one fluorine atom that will overlap with the other. So if I draw that one p orbital that is incomplete for each fluorine atom with the dot representing the nucleus, so this end of the p orbital that is incomplete in one fluorine atom will overlap with this end to form an end-on overlap to form a sigma bond, right? So when these two get together, what happens is, to form a better overlap, the shape of the p orbital, which is right now hourglass shaped, is going to change a little. The end that is not overlapping is going to become small. It's going to shrink. The end that is overlapping will become larger so that there is better overlap of the p orbitals, right? And so the bond pair resides in this large overlapped region, which is the sigma bond, and these two nuclei of the fluorine atoms will attract the bond pair towards themselves, and this is what is called your covalent bond. These force of attraction between the two nuclei and the bond pair shared between them, right? And by the way, this changing of shape of the p orbitals to cause it overlap is called hybridization, and we will cover this in a future video. So the next case is the overlap of an s orbital with a p orbital, for example in HF, hydrogen fluoride. So if I have a hydrogen atom with a 1s orbital that is spherically shaped, which bonds with a fluorine atom that has a p orbital that is dumbbell shaped or hourglass shaped, that is incomplete, then what happens is that if I divide this s orbital into two ends, this end will overlap with this end to form a sigma bond. So this looks something like this. So I have a positive nucleus here of the fluorine, positive nucleus here of the hydrogen, and in between I have the bond pair of electrons that are attracted to both nuclei, right? And over here you can see that the p orbital in the fluorine atom, it changes shape so that the end overlapping with the s orbital of the hydrogen can overlap in a better way by providing a greater area of overlap. So this is the sigma bond. So the next kind of covalent bond is the pi bond, and it is formed by the side-on overlap of atomic orbitals, and these are usually p orbitals, right? So we won't be discussing s orbitals in pi bonding. And for a pi bond to exist, there must be a sigma bond between the two atoms already, right? So I'll explain this using a couple of examples. First of all, we have oxygen, right? We know that oxygen, from the previous video on covalent bonding, there is a double bond between the two atoms, right? So what happens basically is that you have the two atoms of oxygen, and first of all, there is a sigma bond formed between them using the overlap of two p orbitals end on, right? So they change their shape. The end that does not overlap becomes small, it shrinks. The end that does overlap becomes large so that there is a greater overlap to form a better molecular orbital. And then we have the bonding pair between the two nuclei that attract it towards themselves, right? So you have your oxygen atom here and over here. Now what happens is there's going to be a double bond formed by not just the end-on overlap of two incompletely filled p orbitals, but the side-on overlap of two further incomplete p orbitals. So we know that the p subshell consists of three p orbitals, one along the x-axis, one along the y, and one along the z-axis, right? So I've shown you the p orbitals along the x-axis overlapping. What if I showed you the incompletely filled p orbitals along the z-axis overlapping? So what happens is I have an orbital along the z-axis over here and over here, right? And what happens is this end will overlap with this end to form a pi bond. And this end over here below the axis of the sigma bond will also overlap with this end of this p orbital below the sigma bond axis. And so both ends of these p orbitals are overlapping both above and below the sigma bond axis, right? And so this forms your pi bond. This over here is your sigma bond, and this both above and below is your pi bond, right? So you have a sigma bond and you have a pi bond in place. So this forms your double bond. Now finally, in the case of nitrogen, the unreactive gas I talked about earlier, now the reason why it's unreactive is because it has a triple bond between the two atoms, right? And how this is formed is basically that you have two nuclei. First of all, you form a sigma bond between them using the change in the shape of the p orbital. The end that overlaps will become larger, the end that does not becomes smaller, and you have a sigma bond right here, right? Now you have a pi bond forming by the overlap of the two incomplete p orbitals along the z-axis, as I mentioned earlier in the case of oxygen, right? And now there will be something happening further. I will now draw the incomplete p orbitals along the y-axis for each of these nitrogen atoms. So I'm going to draw one over here and one over here, right? These slightly tilted p orbitals that overlap over here and over here, right? So you can see that there is one sigma bond and there are two pi bonds being formed, right? Both above and below the sigma bond axis, right? So remember that whenever you have a single bond, such as in fluorine, you will have one sigma bond. If you have a double bond, for example, in oxygen, you will have one sigma and one pi bond. And in the case of nitrogen, you will have one sigma, that's always the basis, and then you will have a further two pi bonds being formed, right? So remember that because there are three p orbitals, one of them will form a sigma bond, and the remaining two can form up to two pi bonds depending on how many of them are incompletely filled. All right? And so it's because of this one sigma and two pi bonds in nitrogen that nitrogen has such a strong triple bond, and so it is unreactive because of the strong triple bond, and that is why you see so much of it packed into a bag of chips. All right? So this was all about sigma and pi bonds. If you have any questions, do comment below. And if you like this video, do like it and share it with your friends. Subscribe to Conquer Chemistry for more videos. And inshallah, I will see you in the next video.